Hello, welcome to lecture 18 for EME 172. So last time in lecture 17, I finished up root locus examples. So that's the last of the material from chapter 8. And today I'm going to talk about material from chapter 9. So this is using the root locus to design controllers. And I'll remind you that the homework 5 is due Friday before 5, and homework 6 is going to be due next Friday. So designing controllers. There are several different kinds that we're going to learn about. So we already know the names, but I'll write about what their characteristics are. So we have a PI controller, that's proportional integral control. And the idea is that we add an integrator. That's a pole at s equals 0. And what does this do? It helps us to have low steady state error. So it will improve our ability to track a reference input or to equivalently to reduce the steady state error. And if you remember, the idea is that we increase the system type by adding an integrator. So if we have a type 0 plant, when we add one integrator, we make it type 1, and that allows us to track a step input with 0 steady state error. Okay, so that's what a PI controller does. A PD controller, we add damping to improve percent overshoot, actually reducing the overshoot and settling time. And then there's PID control, which combines both of these things together. So we have basically PI plus PD, and so this gives us good dynamic behavior, good transient response in terms of overshoot, settling time, and good tracking, or low steady state error. Okay? So these are really the three types of controllers that are sort of dominant, right? So PID is sort of the most common one that we'll learn about. There's some other ones that I'm going to talk about, and those approximate PID control. Okay, there's what's called a phase lead compensator. And this basically approximates a PD controller. There's a phase lag compensator. This approximates a PI controller. And then there's also a lead lag compensator. And this approximates a PID controller. Okay, and I'll talk about today, the things I'm going to focus on are PD, so the proportional derivative control, and I'll talk about phase lead compensator as well. Okay. All right. Now, any of the controllers can be used either in the forward path or the return path of the feedback loop. So like this. So we can either have what's called cascade compensation. So cascade means that the controller is here, the plant is here, here's the reference, here's Y, or what's called feedback compensation. So in feedback compensation, we have the reference coming in here. Here's the plant. And the feedback controller is in the feedback path. Okay, so you may see both of these kind of configurations. It turns out that they have the same closed loop characteristic equation. So the poles are the same. So both have the same closed loop characteristic equation, which is going to be 1 plus GP GC equals 0. So therefore they have the same poles, but the zeros will be different. They're different. And another way to sort of reason this out is that when we do cascade compensation, it turns out that if we think a very simple version of cascade compensation, where we have some gain k here, and here's the plant, and we just think about the plant as having some amplification or gain a, like this, right? So this is just a very simple example. We could write the transfer function from r to y as ka over 1 plus ka. And when ka is big, right, so these are just numbers, okay? K could be 10, a could be 1,000, right? So then the product of those two things is 10,000. Then we could write that y over r is more or less equal to ka over ka, which is 1, okay? Right? So if the product of the controller gain and the plant gain are much bigger than 1, then if we look at this transfer function, it looks like a 1, which is, you remember what we want to do, right? We're going to put in a reference signal, reference input, and we want y to be exactly equal to r. Now, if we have the feedback system, this is not true. So here's the plant gain. Here's the controller gain. And so it turns out that when we write this transfer function y over r, we get a over 1 plus ka, which is approximately equal to a over ka, which is just 1 over k. Okay, so it's clearly not 1. And the bigger we make k, the smaller we'll make y. Okay, and so often what we'll do, so this is perfectly, it's still a reasonable controller, but we have to do something to scale the input signal. And so this is a little bit undesirable, and this is one of the reasons why we often use this cascade compensation approach. Now I'll comment that and some of you, basically, this is more important for folks who are thinking about studying controls in graduate school or maybe seeking a career in this, is that the drawback, if we look at the cascade compensator versus the feedback compensator, is that we'll see that the controllers have some dynamics. They're basically like a filter. In some cases, they're like a low-pass filter. And so if we have a reference signal, let's say this is a step input, and it changes, so it changes really quickly, then the plant can't know about that until the signal propagates through the controller, okay? So in this cascade compensation scheme, it's going to take a while for that reference to reach the plant. And so it may be that the response to a sharp input is going to be slow. And so there is a way around this, however, and that's to use what's called feed forward, a feed forward term. So what we can do is we can actually inject the reference here, and we can also inject it. I'll draw a little picture here. So here's the reference signal. Here's the controller. Here's the plant, right? Remember, we know the reference signal. We're generating this input to the plant, right? This is the output of the controller is U here. And so what we want to do is we want to avoid the time delay that it will take for the signal to propagate from the error to you, right? So whatever the time delay is through this controller. So what we can do is we can take the reference signal and we can actually inject it here as well. So we can put it in here to generate the error, and we can also have this other term here. And so this kind of a loop is called feed forward. Okay, so I won't ask you anything about this on the homework. It's not going to be on any exam or anything, but you may, those of you who study controls later on in life, you'll hear about feed forward compensation or a feed forward term. And so this is the idea of the feed forward, is that we take the reference signal, we inject it here to create the error signal, but we also add it directly to the output of the controller so that we get faster response from the closed loop system, so that we immediately get a step input going into the plant. Okay. All right. So what I'm going to do is, sort of without further ado, I'm going to talk about PD design example. And before I really get into PD, I'm going to, so let's just talk about the physical system. So the plant here is going to be a translation stage. So it's a translation stage. Okay. And the dynamics for this thing is we have a moving sled sort of sliding on bearings. It has some mass. It's moving here, and I apply a force. And there's some bearing friction. Whoopsie. So there's some bearing friction from these guys. And that's equal to B times x dot, my usual linear model. Okay? So the equations of motion here are sum of forces is equal to m times acceleration. And so that's equal to the input force minus b times x dot. Okay? So it's simple equations. I get mx double dot plus b x dot is equal to the force. Or we could, if we take the Laplace transform, we'll get x of s is equal to 1 over ms squared plus b times f of s. Okay, so this is the transfer function from input force to output displacement. That's right, this is there should be an s there. And so what we can do is sort of visualize this as being force going into a first order system. So here's the force. It's coming out as velocity. I'll write it as v. And then we integrate that to produce the position. Okay, so this block here is 1 over ms plus b, force to velocity, and then we have one extra integration to get us to position. Okay. So now what we want to do is we want to have like a desired position. Okay, that's our reference signal. We're going to measure the position and we'll compare it to the desired position. Like this, that produces the, here's the minus, here's the error signal, okay? And I have a controller here, okay? So this is the plant, GP of S. Okay, so this is a motion control system. It looks probably familiar. We've seen these things before. Now, often what we want to do is we were going to have some specification about the steady state error, okay? And if you remember when we talked about steady state error, so let's say we have like a step reference input. I'm going to actually pause and I'll continue this in the next lecture.